Welcome to this session. This session is have 3 problems to solve. So the first recurrence relation is an equals to an minus 1 plus 2 an minus 2. The initial conditions a02 and a17. Second recurrence relation is an equals to 6 an minus 1 minus 9 an minus 2. With the initial conditions a01, a16. And the third recurrence relation is an equals to 2n minus 1 minus 5 an minus 2. With the initial conditions a0 is 1 and a1 is 5. So let's start by the first recurrence relation given by an solution. So solution. So the first recurrence relation is an is given by an minus 1 plus 2 an minus 2. That is what we have been given in the first case. So the first, we assume that the solution to this recurrence relation is an equals to r power n. So let an equals to r power n be the solution. So then an minus 1, this implies that an minus 1 will be r raised power n minus 1, and an minus 2 will be given by r raised power n minus 2, just using this definition. So if I call this one equation 1, this one equation 2, so replacing 1 in 2, 2 in 1, we have, remember the assumption here is that r is a non-zero constant. So r power n is equals to r raised power n minus 1 plus 2 r raised power n minus 2. Since r is not 0, then divide through by r raised power n minus 2. This will give us r squared equals to r and then plus 2. And then on rearranging, we'll have r squared minus r minus 2 equals to 0. This is what we call the characteristic equation. So let's see whether we can factorize this one. So product is minus 2, sum is minus 1. So the numbers should be negative 2 and 1. So this quadratic will be r squared minus 2r plus r minus 2 equals to 0. So it'll be r into r minus 2 plus 1 into r minus 2 equals to 0. And so r plus 1 times r minus 2 equals to 0. This means that r1 is taken to be negative 1 and r2 is taken to be positive 2. So these are cases whereby we have two distinct roots of the characteristic equation. And so the general equation, the general solution is given by an, given by c1 r1 power n plus c2 r2 power n, which is the same as c1 r1 is negative 1 power n plus c2 r2 is 2 power n. So we have the initial conditions in this question that A naught is given by 2 and A1 is given by 7. So when you say N naught to mean that the value of N is 0, so this means C1 negative 1 power 0 plus C2 2 power 0 is what gives us 2. Now when you simplify this one, you'll get minus 1 power 0 is 1, so it will be C1 plus 2 power 0 is 1, so will be C2 equals to 2. Call this one equation 2. And then this will be A1 means N is 1, so we'll have C1 minus 1 power 1 plus C2 2 power 1, which implies minus 1 power 1 is minus 1 times C1 is minus C1 plus 2 power 1 is 2 by C2 is 2C2. That will give us 7. Call this one equation 3. Now we solve equation 3 and 2 to get C1 and C2. And the easiest way to solve this one, let's just use elimination. So by adding these two equations, we'll get 3C2 equals to 9. So which means C2 is 3. So from 1, C1 is 2 minus C2, which will be 2 minus 3. So therefore, the value of C1 is negative 1. The value of C2 is positive 3. So therefore, the particular solution, the specific solution, is AN. So this one is negative 1. This one is positive 3. So I can write it 3 2 power n minus 1 power n. So that will be the solution to that given recurrent relation. Part B, we have AN equals to 6n minus 1 minus 9n minus 2. So B, we have AN equals to 6, AN minus 1 minus 9, AN minus 2. So we let AN equals to RN be the solution. So this means that AN minus 1 will be R raised to n minus 1 and AN minus 2 will be R raised to n minus 2. So using these values in this recurrent relation, so we call this one 1, call this one 2, then R power n, so replace 2 in 1. So where there's this, we put R power n equals to 6, R power n minus 1 minus 9, R raised power n minus 2. And then this R is non-zero constant. So dividing through by R raised power n minus 2, R raised power n minus 2, R raised power n minus 2, this will give us R squared equals to 6R minus 9. On rearranging, we'll have 6R squared minus 6R plus 9 equals to 0. Now product is 9, sum is minus 6. So numbers must be minus 3 and minus 3. So this quadratic will be factorized as R squared minus 3R minus 3R plus 9 equals to 0. So common here is r into r minus 3. Here is minus 3 into r minus 3 equals to 0. So r minus 3 times r minus 3 equals to 0. So this means that r equals to r1 equals to r2 equals to just positive 3. So these are cases of a repeated root, and the general solution for that case, the general solution is an c1 r power n plus c2 n r power n, which will be an equals to c1 3 power n plus c2 n 3 power n. But the same problem, we are given the initial conditions that a naught is 1, a1 is 6. So a naught is 1 and a1 is 6. So this means that where there's n in this general solution, we put 0. So we have c1 3 raised to power 0 plus c2 times 0 3 power 0. This will be c1 because 0 times every term here will be 0. So which implies that c1 will be 1. And then a1 means the value of n is 1. So put 1 here. So c1 into 3 power 1 plus c2 times 1, 3 raised to power 1. This will be 3c1 plus 3c2. This equals to 6. But because we know c1 is 1, so we'll have 3 times 1 plus 3c2 equals to 6. So we'll have 3c2 equals to 6 minus 3, which is 3. So c2 will be 1. So therefore, the specific solution or the particular solution for that problem will be given by an is given by, so you see c1 is n is 1 and c2 is also n, so just be 3 power n plus n 3 power n. So that would be the solution to that given recurrence relation, because here is 1, this also 1. And then finally, we have to solve the recurrent relation an equals to 2 n minus 1 minus 5 n minus 2. So a, this is c, n is given by an minus 1, 2n minus 1 minus 5, an minus 2. So solution, you assume or let an equals to r power n, where r is a non-zero constant, be the solution. Now, once we have fixed that, then that means an minus 1 is r raised to power n minus 1, and an minus 2 is r raised to power n minus 2. So if we call this equation 1 and call this one equation 2, then substitute equation 2 in 1. That means you change now this recurrent relation from ai's to r raised to power i's, i.e. this will be r power n and then 2 r minus r raised to power n minus 1 minus 5 r raised to power n minus 2. And since R is a non-zero constant, we can divide through R raised power n minus 2, R raised power n minus 2, R raised power n minus 2. So which means we'll have R squared equals to 2R minus 5. Now we can rearrange this quadratic as R squared minus 2R plus 5 equals to 0. So this is what we call the characteristic equation. So we use quadratic formula to solve this equation. So R is minus B plus or minus square root of B squared minus 4AC divided by 2A. So which will be 2, because minus 2 is 2, positive. Minus 2 squared is 4, minus 4 times 1 times 5 is 20. And then 2A, A is 1, so this will be 2. So R will be 2 plus or minus square root of minus 16 divided by 2. Square root of minus 16 is minus 4i. These are complex root. So this will be 2 plus or minus 4i divided by 2, i.e. R equals to 1 plus or minus 2i. So which means you can say R1 is 1 plus 2i and R2 is 1 minus 2i. So this is a case where we have complex roots for the characteristic equation. So solution, general solution is an equals to C1 R1 power n plus C2 R2 power n, which will be C1 1 plus 2 I power n plus C2 1 minus 2i power n. That's by definition. So because we have been given initial conditions, then they will help us to find the specific values for C1 and C2. So we have been given that A naught in this question is given by 1 and A1 is given by 5. So what we do, we replace 0 for n in this equation. So we'll have C1 1 plus 2i power 0 plus C2 into 1 minus 2i power 0. And you see any number raised to 0 apart from 0 itself is 1. So this is 1, this also 1. So this implies C1 plus C2 is 1. So call this one equation 3. And then this will be the same as C1, 1 plus 2i raised power 1 plus C2, 1 minus 2i raised power 1. This implies C1 plus 2i C1 plus C2 minus 2 C2i is equals to 5. Call this one equation 4. But you see, we know that C1 plus C2 is 1. So this equation 4 can be written as C1 plus C2 plus 2iC1 plus minus 2C2i is equals to 5. So this part we replace by 1, and then that means we'll have 2C1i minus 2C2i is 4, because we take this one to the right hand side. So dividing through by 2, we'll have C1i minus C2i is equals to 2. So we can now say, even from this given equation here, C1 is the same as 1 minus C2. So when I say 1 minus C2 times I, so I'm replacing C1 by this, then minus C2I is equals to 2. So this would be I minus C2I minus C2I equals to 2, which will give me minus 2C2I equals to 2 minus I. And then I can divide through by minus 2I, divide through by minus 2I, which is the same thing as writing. So this implies that C2 will be 2 minus I divided by minus 2I, and then we multiply by the conjugate of this is positive 2I, positive 2I, so which will give me, this will be 4I, I times I is minus I squared, which is minus 1 times 2 is plus 2, divided by this will get 2 times 2 is 4, I times I is I squared, which is negative 1, but negative is plus, so this is 4. So 2 is common, so divide through by 2, C2 will be 1 plus 2I, and then divided by 2. So that is what we get as our C2, and C1 is given by 1 minus C2, which will be 1 minus, so this can be written as a half, and then plus I. So which is the same as 1 minus a half minus I, which is a half minus I, which is the same as 1 minus 2I. So that's the value of C1. So therefore now we say the general solution, the specific solution. So therefore the specific solution or the particular solution is the value of C1 is 1 minus 2I over 2, and then we multiply by 1 plus 2I power n, plus C2 is given by 1 plus 2I divided by 2, and then 1 minus 2I power n. So that's what we have. And then, so this is the solution, the particular solution for our given recurrence relation. Or you may decide to rationalize the numerator by, okay, so this is what we can have, or you can simplify it further if you like for this complex part, but this okay. Or in this case, you can say in this given equation, if you factor out 1 minus 2I, and then times 1 plus 2I, and then you say divided by 2, divided by 2. Then here, because I have already factored out this one, so I'll have 1 plus 2i, and then I need to multiply this one by. So now that, okay, let's just do step by step. For this one, we can simplify it further by saying that so 1 minus 2i over 2 multiplied by 1 plus 2i equals to, so 1 plus 2i power n. So because I have factored out, I put, to get back my original expression here, 1 minus 2i over 2 times 1 plus 2i raised to power n, then I need to divide this one by 1 plus 2i. And then plus, this one is already out, so I need to have 1 minus 2i power n divided by 1 minus 2i. This is still the same expression. Now this is a difference of 2 squared, so you have 1 squared minus 2i squared over 2. So which will be given by 1 plus 4 over 2, which is 5 over 2 into 1 plus 2i power n divided by 1 plus 2i plus 1 minus 2i over 1 minus 2i power n. So we can as well write this one as 5 over 2 into now 1 plus 2i, now say n minus 1 plus 1 minus 2i n minus 1. So we can as well write the solution this way, or just leave it at this point, there's no problem. That's how we solve that particular question. Thank you.